Right, good morning, good afternoon, good evening. Class, this is Mr. Arosena, and today in physics we're going to talk about work. Now, in science, I guess in physics in particular, work has a specific meaning. Okay? It's not the same as like the work you do in like say at home or the work you do for other classes or things like that. Work in physics has an actual specific meaning. Okay? So in physics, work is defined as the product of force and distance. So work is equal to force times distance. And we can describe it in a simpler formula with W equals Fd. Now, in order for work to be done, two things must happen. One, there must be a force acting on the object. And two, the object must be displaced in the direction of the force acting on it. So for example, if you are trying to push on a wall, if you guys are beside a wall, you can attempt this right now. Push on the wall. You are applying a force, but the wall isn't moving. So even though you're applying a force, because the wall isn't moving, you are not doing any work at all. Okay. Similarly, if an object is moving but there's no force being applied to it, like for example, if you are floating in space or flying through space and there's no force acting on you, then no work is being done on you as well. Okay. So in order for work to be done, there must be a force acting on the object and the object must be displaced in the direction of the force. And this part becomes quite a bit important. Direction of the force. Okay. All right. So in the first example, sounds pretty easy. Here we have a box, requires a force of 50 newtons to push it along a surface. If it is pushed for 2.5 meters, how much work is done? So a very easy, simple example. We have our force, 50 newtons. We're going to push it a distance of 2.5 meters. So the amount of work done is going to be force times distance. Is going to be 50 times 2.5. This will be a 125 Newton meters. There we go. Newton meters. That's our unit for work, is Newton meters. Now, usually we actually change this to another more familiar unit, joules. Okay, so 1 Newton meter is equivalent to 1 joule. All right, so that's a quick example of how we can use force, or how, use force to figure out how much work is done. Okay. All right, another example. So there we had, in that previous example, we had the force explicitly given to us. This example is slightly harder. The force isn't going to be given to us explicitly. So how much work is done when lifting a 2.5 kilogram chair a vertical distance of 1.2 meters? Okay. So the amount of work is still going to be force times distance, but this time we're not explicitly given how much force is needed. Okay. But if you think about it and ponder it for a short while, you should be able to figure out what the force is. So my suggestion is like just pause the video for a moment and think to yourself, what force is being used to lift this chair? All right. If you paused it or just thought about it while I was talking, then you should realize that the amount of force needed to lift this chair has to equal at least the force of gravity. So the force of gravity we know is going to be 2.5 kilograms times 9.8 Newton meters per second, or that's not the unit, what's the, newtons per kilogram, sorry, newtons per kilogram, or meters per second squared, times 2.5. So this will end up giving us an answer of, let's see, 2.5 times 9.8 times, oh wait, it's only 1.2 meters. This should only be 1.2 meters. My mistake. So it should be 1.2 times 1.2. So altogether we get 29.4 Newton meters, or 29.4 joules. There we go. All right. So there in this example, the force wasn't explicitly stated, but with a little bit of thought, we were able to figure out just what force we needed to apply to lift this chair a vertical distance. All right, next example. So in this example, we have a 52 kilogram student walking up a flight of stairs that is a vertical distance of 5.5 meters. How much work does the student do? All right. Well, here, so we have a 55 kilogram student. The going in a vertical direction suggests, and this should be 5.5 meters, going in a vertical direction suggests then that the amount of work we do is going to be the same as the previous example. Force of gravity times distance, which it turns out is actually correct. Because since we're moving a vertical distance, the force needs to be applied in a vertical direction. And that vertical direction has, or the vertical force has to overcome the force of gravity. So we can calculate the work done similarly to the previous question, where we take our mass times g times a vertical distance of 5.5, and this will give us, slide this over here, 52 times 9.8 times 5.5, 2,803, I guess. 2,008, or sorry, 2,080, or it's 2,800, jeez. All right, 2,803. 2,803 joules of work needed to lift your body up 5.5 meters. Okay, and this is the same whether you go up a set of stairs or whether you climb a rope. You still need to do that much work. Okay. All right. Okay, so in this example again, the force that was needed wasn't explicitly given to you, but with a little bit of thought, you realized, okay, well, I'm moving a vertical distance, so the force I need to overcome must be a vertically oriented force, and the only vertical oriented force in this situation is the force of gravity. All right, this last example shows us, if you remember from the last lesson where we talked about forces at an angle, and how if you push down on something, it actually increases the amount of friction. Well, this example illustrates why that is important, or what that does to a problem. So here we have a lawnmower is being pushed by a boy applying a force of 100 newtons at an angle of 60 degrees to the horizontal. How much work does the boy do if he pushes the mower 5 meters? All right. Okay, so we'll assume this first bit as being frictionless, just to make our problem easier. So we'll assume frictionless, so mu is equal to 0. We'll assume frictionless, which we all know is not true though. We know friction. We know this is not true, and if you've ever pushed the lawnmower around, then you know that there is going to be some friction. All right, anyways, remember what I said about work being force times distance? Well, this force must be in the direction of motion. Direction of motion. Okay, so the force must be in the direction of motion. So in this case, this 100 newtons since it's being pushed down, not all of that 100 newtons is going to be used to move the lawnmower. So what we need to do then is figure out, well, if the lawnmower is moving in this direction, we need a force that's also going in this direction. All right, so let's draw my force going down. Probably like this. There we go. The force that's the part that we want is going to be here. So there we go. There we go. So the force that we want is going to be the x component of my 100 Newton force. Right, so this is 100 newtons, so we want the x component. Right, and then this is 60 degrees. So we want this. Well, to figure this out, we can do, okay, this is just a right triangle, so we can use x happens to be the adjacent side, so we can say the following. cosine 60 is equal to x over 100. Bring the 100 over, so we get x is equal to 100 times cosine 60. So this will be, where's my calculator? So 100 times cosine of 60 equals 0.5. Oops, that's not right. 0.5 times 100, so equals 50. There we go. So x is equal to 50 newtons. All right. Now we can calculate the work, because we have the force, the useful amount of force. So work is equal to force times distance. In this case, it was the x force. So 50 times, I think we're pushing 5 meters. 5 meters. 5 meters. So altogether, it's causing 250 Newton meters of work, or 250 joules. All right. There we go. Now, even though the boy is applying 100 newtons of force, only 50 newtons of it, according to our triangle, only 50 newtons of it is actually being used to push the lawnmower. This y component here, so the y component is actually pushing down. Now, why is that important? Well, if we did not have a frictionless surface, then let's just go back here. If the surface was not frictionless, then you would have a friction force opposing you in this direction. And as we remember from the last lesson, friction force is mu times Fn, where Fn is the compressing force. And if you're pushing down on the lawnmower, you're actually adding more compressing force, which means your force of friction is going to be greater, which means that you'll actually be doing even a less useful work, even a less useful force than you would if it was a frictionless surface. So if you are ever moving anything, you kind of don't want to be pushing down on it, because it limits the amount of work, or limits the amount of force you can apply, and makes the friction you have to overcome a lot larger, because you are pushing down on it. So this y force that pushes down, it increases this force here, and really makes your job a lot harder. All right, so there you go. All right, so that's work. Work, again, force times distance, but force must be in the direction of the motion, right? So work, force times distance, and this has to be in direction of motion. In direction of motion. Okay, so be mindful of that when going through the assignment. Speaking of which, your assignment for today is as follows. Just very simply, complete the worksheet. Okay, have at it.